Yeah, what is going on with that? This is on? Yes. Good afternoon, everyone. I hope everyone is still awake despite the lack of coffee during the break. Um, and we only have a couple more hours to go before the real break. Less than that, an hour and a half or something. But we have two very exciting talks coming up, and the first of them is Natalie Hinkel from Louisiana State University. However, before she gets started, I'm I guess a spokesperson for the event that may or may not happen this evening, which is stargazing at the planetarium at the Los Alamos Nature Center, the Pajarito Environmental Education Center. If it's clear, we'll be out there with telescopes, and even if it's not clear, we'll probably be out there with our telescopes under the portal. So come on out, and if it's not clear at all, and if it's raining or whatever, I'll have the opportunity to give you a planetarium tour of Mars and Jupiter. We have models of all of these all of the solar system objects, and I've even scripted up some things where we can drive through Valles Marineris and some other places. So that could be fun if and we can do other things in the planetarium also, of course, and we also have the option of doing some of that tomorrow afternoon. So that's a little bit of a spiel for me, which is entirely independent of Natalie's talk, and also has allowed a few more people to come in, for which both Natalie and I are extremely grateful. Right. So without any further ado, I'll ask Natalie to tell us about the chemistry between stars and their planets. This sounds very suggestive.
That was the intention. Thank you very much, John. And thank everybody here who invited me here. Thank Lionel, CSES, the consortium, everyone. I'm so excited to be back in the desert. I've missed it heartily. I'm now at Louisiana State University, where the outside continually tries to kill me. A little bit about me. I'm thank you. I am married to Dr. Caleb Wheeler, who now works at the LIGO Gravitational Waves Observatory. He was originally a cryostat engineer. We have two wonderful cats, one of whom might actually be older than some of the people in this room. She is 20 years old. And then Lasagna. For my history, I went to Oberlin College, where I was a math and physics major. I was one class away from a minor in theater. Then I went to Arizona State University, where my degree is technically in astrophysics, but I learned from my geologist friends and cohort. I actually call myself a planetary astrophysicist because that actually describes what I do. With that, I've also moved a lot. So if you are from any of these cities, I'm happy to talk to you about them. I've lived basically all over. All right, so starting actually from the beginning, let's talk about exoplanets. So exoplanets are planets that are outside of our solar system, exoplanet. And as Dr. John Grunsfield mentioned yesterday, the first exoplanet that people really think about and consider an exoplanet was discovered in 1995. Now, actually, the first ever exoplanet was discovered in 1992, but nobody believed it. They didn't care. They thought it was actually a very, very tiny star. And so they just ignored it until the 1995 discovery, which won a Nobel Prize. And so what you're seeing here is all the discoveries that we've detected since that time. To date, we have 5,876 exoplanets. And you can see how we've detected them, the various ways that we've detected them. It's also really clear from the increase in time that certain missions were incredibly important. So you can see where Kepler came into play and then the TESS mission. And so now we have a huge number of planets. And this is fantastic. I get most people in here are planetary scientists and they're super focused on the 8. But I really like the other ones. So and the reason is because, so this is an orrery. It actually shows the 4-scale size of the different architectures of exoplanetary systems. Now, this is old, but it still gets the point across. So you can see that there are big planets that are near their stars. There are small planets far away from their stars. You can see that there are big stars and little stars and big planets and medium-sized planets and planets that we don't even have in our solar system. And so I love showing this. I love showing this because it really gets across the infinite diversity and infinite combinations that we see in our planets. And for you Star Trek fans, yes, that was an intentional IDIC reference. And so here we can see like all the different varieties of the different kind of planetary systems. And that's exciting for me because what I'm trying to see is where we could possibly detect habitability or have habitable planets. And so when you look at all these different kind of systems in their different architectures, you get all these different places where you could potentially have habitable life or habitable planets. Okay, so here are some examples so you have something to actually hold on to. So what we're looking at here on your left is a planet that's tidally locked. So much like our moon, only one side of the planet is facing the star at a time. And so you have a very hot day side, a very cold night side. Now, just because something is tidally locked, that doesn't mean it's not habitable. You could have the sort of thin strip in the middle where you'd have mixture of the hot and cold temperatures where you could potentially have some kind of climate that's actually conducive to life. So that's pretty cool. Now, above me is a moon around a planet outside of our solar system. So this is an exomoon. So it might be that the planet itself is not actually habitable. It could be a gas giant. It could actually be outside of what we refer to as the habitable zone. But the moon itself could be habitable. And so that's another place where we could potentially look for life because these moons actually get heat not only from the sun, but also from the planet. And so they could be at temperatures that are conducive to life, which is actually pretty exciting. And if we think that there's a lot of planets out there, holy hell, there's a lot of moons. Okay, and then finally on your right, we have planets outside of that are orbiting stars that are not really like our sun. These are called M-dwarf stars or red dwarf stars. And so what they receive, the light that they receive is not going to be yellow like what we get from our sun, but it's actually going to be red. And so just because these planets sort of get a different kind of light, and they must also be much, much closer to their star in order for them to be the temperatures that are conducive to life as we know it, that doesn't mean they couldn't be habitable. In fact, this is a topic that's near and dear to my heart, which I will not be going into, so if you're interested, please ask me questions. Okay, now, all of this is to say that habitability is extremely complicated. And I come at this more from an astronomy perspective, where I'm actually trying to get sort of the holistic idea, so the entire picture of a planetary system, what goes into all the various properties. So to really give you a clear idea of how we get here, I'm going to start from the beginning. And by that I mean the Big Bang. Okay, when the Big Bang first happened, the only elements that really existed in any real quantity were hydrogen and helium. So there's nothing else, no oxygen, no iron, no silicon, nothing. But the universe, it's not flat. It actually has bumps and wiggles in it. And so because of that, all the gas that's in the universe actually sort of starts coming together. So forms in these big gravitational pockets. And so you get big enough pockets that have huge amount of gas in them, and they eventually gravitationally collapse in on themselves, and they form the first stars. Now, these first stars are the first place that have the ability to have fusion. So in their core, they have hydrogen and helium, but because they have the pressures and densities that are exactly what you need, you can form the next level of stars. You can form, elements. You can form heavier elements. So now we don't just have hydrogen and helium in these stars, we get little seeds of carbon, we get seeds of silicon and things like that. Now these big stars, they're about 100 times more massive than the sun. A comparison is like a fat cat to a grape. And so they live fast, they die young, the stars, not the cat. And they explode. And also when they explode, they create new elements within the explosion. So they send all these new elements to different parts of the universe. And so the next generation of stars sort of scoops them up and form new stars. Now, they build off of these seeds of the carbon and the silicon and the iron, and they start forming heavier and heavier elements. So over multiple generations of stars, we get most of the periodic table. So this is an awesome, awesome plot that I really love to show. This was created by Jennifer Johnson. It was literally the first time that it was done was on a napkin, as all good ideas are. And so it shows you in a color-coded way where we get all these different elements, some of them from Big Bang, some of them from different kind of stars that are colliding with one another, some of them for just stars dying in the variety of ways that stars love to die. And so this is super, super exciting because it shows like where we get all of different elements that make us, that make Earth, Earth, and all the different planets in between. Now, what I do is I actually try to look at the composition of these stars. So we use a technique called spectroscopy, where light comes out of the star, and it runs into some of these elements that the star was made up of. And it's actually these elements were at the top layer, which harkens back to the initial birth cloud that these stars formed from. And so when the light exits the star, it runs into, say, a nitrogen atom. It absorbs some of its light, and we're able to see that. We're actually able to see the little absorption lines in the star spectra. We flip that around, and we get these little dips in the spectra. Literally, you have more nitrogen, the bigger the dip. It's fairly simple. Then from kind of basic calculus, where you calculate the area under the curve, we are able to calculate the total amount of nitrogen that must be in that star based on how big that dip is. So we can get the actual element abundance, it just means amount, so abundances just mean amount, of an element within the star. Now, what I've done is I've created the largest database of elements within stars that are near to the sun. This is called the Hypatia catalog. It currently has 13,000 stars covering 100 elements that I've collated from 340 data sets. I did this, just me. This is actually something, thank you. And for the VIPs who have stickers, now you know what these stickers are for. This is something I started in 2010, got published in 2014, was a website in 2018, and now everybody has access to it. In fact, NASA takes my data, because I'm badass. And so what I've done is this is just a plot of all of the different elements that we have in nearby stars. So you can actually see all the elements that like people really focus on, or that it's kind of easy to do. And I'll come back to this actually near the end to show the things that are actually quite important. Now everybody asks, so I always like to say, the Hypatia catalog is named after Hypatia of Alexandria. She lived around 400 AD. She was very well respected in her field, in her community. She gave lectures from her house. She talked on math, science, philosophy, obviously astronomy. Super well respected. Unfortunately, that respect sort of got her into some hot water, so she was brutally killed. So I named my database after her because I think she's rather awesome. The movie Agora was based roughly on her. Okay, back to some science. Now, if for people who are familiar with the Magic School Bus, this is a picture of it. Because when stars are created, they're made of dust and gas, they collapse down and out pops a star. But at the same time that a star is formed, you also get planets. Which is to say, stars and planets are formed at the same time and from the same material. And so there's a way for us to use what's in the star as a composition proxy for the planet because they are made at the same time. So when we go and we actually get the abundances of the star, we can use some of those element abundances, the stellar element abundances, and put them into models of the planets in order to have a better understanding of what's going on inside of exoplanets or planets outside of our solar system. And the crux of this really is that exoplanets, super far away. Y'all, they're so far away. I'm actually kind of jealous of like Mars stuff and like you actually get to look at what you do. I do not. So what we have to do, we can't measure the surface composition of a planet, and we sure as shit cannot measure the interior composition. We cannot do that. That's not happening. So we have to use what's in the star as a way to understand what's in the planet, and what's in the planet is so absolutely crucial to what's going on that planet. It really dictates its habitability. I mean, the difference between Earth and Venus is wild, and yet we call them sister planets. So really understanding the characterizations or the different classifications of exoplanets is absolutely fundamental if we're really to understand habitability at all. All right, so let's dive into this a little further. So let's focus on small planets, rocky planets, because really, if we're being honest, this is really what exoplanet scientists care about. We want to find life. And so if you going from star to planet, it doesn't work perfectly. It's not 100%. It's not for everything. Some elements are too volatile. They burn too quickly. They freeze. They do all these things. Carbon and oxygen, perfect examples. We can't go star to planet with that. It's too hard. But we can go star to planet with magnesium, iron, and silicon. And that's fantastic because if we look in our own solar system, the ratio of, which one is it? Iron and magnesium between the sun, Earth, and Mars are all the same within 10%. Like, that's wild. They are vastly different sizes, and they still have these ratios that are actually very similar to one another. But as it turns out, iron, magnesium, and silicon actually make up, with oxygen as a as to bond with them, make up 97% of the materials on the Earth. So if we use iron, magnesium, and silicon in the star, we actually have a very good idea of what's going on in the planet. And that's awesome. That's actually the basis of a lot of my work. And so from that, we're able to really understand the interior composition, the structure, and maybe even the classification of these planets. So let's look at an example. All right, we have the TRAPPIST-1 system. It's there are 7 planets around an M8 star. So M8, so it's an M dwarf, so it's one of those really small red dwarf stars. So this is the system itself, and it is tiny, y'all. It's so small. If we were to put it inside of our solar system, it would be hilariously within the orbit of Mercury. In fact, it's better to compare it to the moons of Jupiter, which is at the top. Like, that's how small this is. Exoplanet scientists were hilariously excited about the system because 3 of the planets ended up being in the habitable zone where we would expect to find liquid water if there was water. Everyone went absolutely apeshit. I cannot tell you how many papers are still being written about TRAPPIST-1, and it was found in 2017. People just go crazy for this because, like, oh my God, they have to be habitable. There's so much stuff going on here. They have to be. And so they continually to like focus on it because it's like the next best place for life. But I actually get a little worried about this because my collaborators and I, we looked at the 3 planets in the middle, the ones that are within the red lines in the habitable zone, and we were like, they seem kind of puffy. Like, if you look at their volume, that's not right. So we're like, there's kind of a lot of water, I think, going on within these planets. So we used the composition of the host star, and we're like, let's make some models of these planets, which is exactly what we did. So we call these phase diagrams. So on the bottom, what you're seeing is like the percentage of the composition of the planet. I sort of think of it as like basically a pie chart that you squash out. And on the y-axis, you're looking at the depth. So at the bottom, you're like, cool, these definitely have liquid iron cores. That makes sense. Great. They have a bunch of different kinds of perovskites, blah, blah, blah. So TRAPPIST-1c, 8 weight% water. TRAPPIST-1f, 50 weight% water. How much water does Earth have? 0.02 weight% water. Y'all, there's so much water. There's so much water on these planets. And people are like, oh, okay, but that's good, right? Like, life on Earth needs water. We love water. We got to have water. Let's follow the water. There's literally been whole research programs called Follow the Water. This, I think, is too much water. This is a lot of water. Because when you're looking at the habitability of a planet, you have to consider the planet as a whole. This is why I think of it as a holistic idea. So if you have that much water, that is miles, kilometers of water. There's so much water. So if you do have life, if there is life, it's probably not going to be at the surface. It's going to be at those boundaries between water and whatever is below it, like the mantle underneath it. So us seeing any signs of that life are going to be very difficult because it won't be a ton of it, because life needs more than just water. Because you need other resources. You need to have these active geochemical cycles that we all come to know and love. Geologists, that's literally their whole life. And we need these cycles to like bring different kinds of minerals around to different parts of the planets. We need to constantly replenish what's going on. But if you have like 50 weight% water, the cycles are going to be very, very minimal. So not only are you not really churning, you're not really able to see the life. And that's important. Like, we need to be able to see the biosignatures for, as Nina talked about excellently, we need to see what might be going on. But if we're not able to see it, then how do we know that it's there? It sort of continues. So we need to have certain kind of planets that we can actually come back to and say, definitively, is this life? Now, when I talk about life, I like to show the equation for photosynthesis. Yes, I'm by nature an astronomer. And I show the equation for photosynthesis in my talks. And that's really to outline that we need certain elements in order for life to exist. So I've highlighted the key ones that we're looking at here. We need 106 carbon to 16 nitrogen to 1 phosphorus. And so that's really the crux here. So that's what we're laying out. You get some other stuff, and then out pops life. Like, this is literally biomatter. And then something I'll come back to. Now, when you're putting this all together, this is actually called the Redfield ratio, 106 carbon to 16 nitrogen to 1 phosphorus. So you smush this all together, and you're like, great, we have life. But then you have to consider how we get the carbon, how we get the nitrogen, how we get the phosphorus. And at the end of the day, it's actually really hard to get phosphorus or phosphate because we have to weather it. It takes time. Actually, a lot of phosphorus is subducted into the core, so it's not even on the surface. Most of Earth's phosphorus is in the core. So what we have on the surface is difficult to get to, and that's kind of a pain in the ass when you want life and you want to have basically the recipe for life. If you make a cake, it's not a great idea to only include half the eggs. It's not good. It's not good. So similar for life, this is what we need. At least this is what we know that we need. So my collaborators and I sort of thought, well, what does this ratio look like when we go outside of the Earth? So we put together sort of rough ratios of plankton, so just as a proxy for life, Earth's crust, bulk silicate Earth, bulk silicate Mars, the sun, and nearby stars. And so this is actually, I could show you to you in the plot, but it's complicated, so I just thought I'd lay it out here. You could just look at the numbers. And so I was so surprised at the variation that's going on between different parts of the Earth, even on Mars. There's a huge amount of variation here. And again, these are not the same elements as magnesium, silicon, iron. These are going to vary during processing, during planet formation, depending on where the planets actually are formed. But the thing that's super cool, very shocking, did not expect this, is that the ratio of carbon to nitrogen to phosphorus in life is actually kind of similar to what we're seeing in the ratio of nearby stars. So the first and last lines, they're a lot closer than anything else. And we're like, oh, this is kind of cool for astrobiology. What if we could actually get a sense of the minimum amount of phosphorus that we might need in stars? So that way, whenever planets are formed around them, some of it will be taken into the core, but some of it might be left on the surface. So this is actually really cool. We're like, oh, that's really exciting. Because again, we want to make sure that when we find life, that we can actually confirm that it's true. So remember in that equation for photosynthesis, there's a little blip that I came back to. So you add everything together, you get biomass out, and at the end you get O2. That's the biosignature. Life creates O2. And so that's what we want to see when we're looking at exoplanets. There are other biosignatures. I'm just using this as an example. So when we look at exoplanet atmospheres, the way we do this is that the planet travels in front of the star. The star's light shines through the planet's atmosphere, and we're actually able to remove the star signature and get a sense of what's going on the planet. So we can see in the atmosphere the composition of the atmosphere. So we can get a rough idea. Let's see, what do we have up here? Molecular oxygen, ozone, water, methane, carbon dioxide. And we've been able to do this. GWST has done this actually really nicely with WASP 96. This is real data, which I think is really cool. The fact that this was the idea behind it, and then this is actually what's going on. So what we're doing is we're looking for signatures of life in the atmosphere, because really it's only exoplanet atmospheres that we're able to directly observe their composition. Again, we can't get the surface, we can't get the interior. But the problem, the real true problem, is that if you are going to say that something is a signature for life, you have to say it did not come from anything else. You have to say it did not come from the interior, from other geochemical cycles, that it couldn't have been produced in any other weird way if you are to say, guys, y'all, we found life. And that's really the big crux of what I do, is because we absolutely, truly have to understand the interiors of the planets if we're really going to understand if there's life, if they could be habitable. And when I say habitability, and I refer to habitable planets, I actually use a kind of looser definition than what Nina does. I say it's anything that could potentially have human-like life, or anything on the Earth, or just anything that we've eventually find could be defined as life. I leave it very loose, because honestly, I don't care. I just want to find it. So extremophiles, yes, please. I'm all for it. But in order to really say that a planet is habitable, it's not enough to just look at its atmosphere. You will hear me railing against the papers that come out. They're like, oh, we found life. Oh, did you? Very confident you did not. Or at least you didn't think about the holistic side of the planet. All right, so this is where we really get into the classification of a planet then. Okay, so like I said, I am an astronomer, like by training. I'm a lot more now. And astronomers, like, they really, like, you know, you try to look at planets, they're so small. It's so hard to measure. You actually have to use a different technique to get an exoplanet's mass than you do for its radius. So when you look at planets outside of our solar system, like I said, there's about 6,000. Only 20% of those planets have mass and radius measurements. That is it. And yet people try to go through and be like, oh, we got the radius, and so we can figure out the interior structure. But I'm like, y'all, there is degeneracy between what is going on the planet and its mass and its radius. For example, the planet that you're looking at the top here, it could have no core, unlikely, but still. It could have just a mantle and core. It could have an ocean. It could have a really thick atmosphere. You could have a bunch of different variations that are going on if you only know the mass and the radius. And this is super interesting and super important as we're especially detecting planets that we do not have analogs for within our own solar system. We have found planets that are super Earths, that are a couple times bigger than the Earth, super Mercuries that are crazy density, but way bigger than our current Mercury, mini Neptunes that are kind of puffy and light, and they might have a giant atmosphere, but they're actually kind of more on par with Earth in terms of their like overall size. And we don't really know what's going on in those. Like, we actually have to set up labs in order to figure out the high pressures, the high densities that might be going on in these super Earths. Because how do we know about the mineralogy when really most of our mineralogy is based on what we understand about the Earth? So this is super important then to really go from what we know about the star to the planet. So we're not just using the mass and radius, but also the star's composition to give us a better sense of what's going on within these planets. And that's really how we go through and get the overall classification of planets and whether they're like these variety of like different kinds. But like I said, we have some gaps actually in our data. So this is an older plot. You'll see it's not at the 13,000, it's like 10,000. And what I've done here is I've color-coded it to show the different kind of elements that are important for different parts of the planet. So some, let's see, what do we got? Blue is the elements that are important for rocks and building planets. And then you have yellow that's important for life. Blue plus yellow is green. So there you go. And what you can really see here is that there are some elements that we know really well. We've measured them very easily in stars. We have tons of them. But there are a handful of elements that are actually very crucial for understanding planets, for allowing life as we sort of understand it to develop. And so those are highlighted here. So nitrogen, fluorine, phosphorus, chlorine, and potassium. We don't know those very well. And the problem with that is that they have a huge, real impact on our understanding of these planets and their life. And so now I'm actually focused on trying to understand and get more actual like element abundance measurements from the stars, or actually influence my fellow astronomers to measure them for me so I can add them in. So like I said, this plot is old. At the time we had 100 phosphorus measurements. Now we have about 300 because people have actually taken up the call and gone through and done it. And this is great because when it comes down to it, when we're really studying exoplanets, it's not just astronomers. It's definitely not just astronomers. It is not planetary scientists. It's all of us. This is one of the most interdisciplinary fields that exists. I work with geologists, astrobiologists, oceanographers, planetary scientists. I work with everybody because I don't know everything about the planet. And it's so important that we do. All right, so let's sort of end on a more positive thing. Okay. Like I said, I work with a bunch of different people. They help me put together this diagram. I'm going to walk you through it in parts because it's actually a little overwhelming. What we're looking at here is sort of a crown of all the upcoming astronomy missions that are going to be launched. And what they're going to measure. My apologies, the key is a little dark. But so say, hopefully, Nancy Grace Roman Space Telescope launches. We will get demographics, direct imaging, the composition of the stars, as well as the planet radius. And so these are all the missions that are coming up. And so this gives us a sense of like, okay, what data is coming? Now what we can do is we can take all this data, all the stellar data that we're going to get about the exoplanets, and we can put it together as a way to really understand what's going on within the planet and the planetary system as a whole. So that's what I'm going to walk you through. So you take a look at these arrows, and they sort of flow out, and it's a way to combine all the data, some of it ground-based, which is what you're looking at down here, but some of them from all these missions, and this is how we pull it all together. Okay, so say that we're looking at the interior processes, which is at the top in an orange. And so say you end up getting the radius, ground-based mass, ground-based stellar abundances. From there, you can get the mantle, core composition, as well as tectonic modes. Okay, but that's, again, not the whole planet. So what if we also then look at the surface and atmospheric processes? And there are some missions like JWST who are really focused on basically that, on just looking at exoplanet atmospheres. So if we get atmospheric composition, that gives us a sense of weathering, climate, volcanism, a lot of other things. And not to think of a planet as being solitary. I mean, like the gas giants did a lot for the Earth on its own. We also need to look at the planetary system. And so we need to see like what else is going on there. Are things stable? Are there sort of like, you know, these big planets that are helping like block asteroids coming towards us? And so we get a lot of information from this. But this was really the breakdown to show you that like this is a wholly interdisciplinary field. On top of that, well, I've tried to lay out, and me and my collaborators tried to lay out all the different things that we can do with all these different measurements. There's actually gaps. There are certain things where there's no data coming for it. So there's room for what we need to understand about habitability, because y'all, habitability is so hard, it's so complicated. We have one data point. So we need all the information that we can. We need all of this information to really get a sense of whether a planet could be habitable. And so it's up to all of, you know, us and in this room. And, you know, this is, I hope, part of the reason why I was invited, because what I do is work with all these different other people to put this together. Like, you can ask me questions about those phase diagrams. I know some. I'm very proud that I can pronounce perovskite. But like, I don't know it all. I was taught the Redfield ratio. I lean on my collaborators because like, this is massive. I do this little chunk. It's like right up here. This is all I do. But it's a huge field. And so like, I'm super excited to be here and to talk with all y'all, especially the VIPs, because like, this is the next step. It's not going to be just me. It's going to be everybody else and people in this room and working all together in the you know, high pressure labs and all these various things so we can get this data together. So at the end of the day, this is what I do. This is the chemistry between the stars and their planets and how all of us need to come together to basically really understand exoplanets and overall habitability. Thank you very much.
Thank you, Natalie. Perfect timing. We have opportunity to ask questions now.
Hi, thank you so much for the lecture. I was wondering, I have my questions written down because otherwise I can't think. Is there an operable suspicion that or hypothesis of how the different stars' lights would give rise to different photosyntheses or photosynthesis-like processes or other ways of like originating that energy in like a energy web?
Okay, so when you say lights, I'm going to take a guess. So what you mean, so for example, with the sun-like stars that have yellow light versus the red dwarfs that have more like red light, is that? Okay, yeah. So the answer is kind of yes, but I don't know fully. So Owamowa Shields, fantastic person, highly recommend looking up her papers. She actually does an excellent breakdown of what life could be like on planets that are orbiting M-dwarf stars, because for that, you nailed it. It would definitely have a different tree of life, web of life, where instead of, you know, going off of optical light, which is something we all take advantage of, but is actually more infrared is what M-dwarfs give off. And so that changes everything. So this is not a thing that I definitively know. I do think, and like I said, I'm actively working on trying to better understand M-dwarf stars. That and people are really apt to sort of poo-poo them, like, oh, you know, M-dwarfs are weird and all the thing, you know, the light's weird, you have to be really close. Some of the M-dwarfs, not all of them, some of them flare, not great for life. But I do think that M dwarf stars could be habitable. But I agree. I think it actually would require a whole different like chain of study to really understand whether or not like how this life might look, how it might evolve. But of course, like we need some data to do that. But yeah, I think it is possible. AOMAWA shields. Yep.
Do you want to say? Can you say a couple of words about Habitable Worlds Observatory?
I can. Thanks, John. Okay, Habitable Worlds Observatory is going to be the next big mission after JWST. I'm actually on the working group that runs the trying to define the target stars that we're going to be going after. So the Habitable Worlds Observatory is still actually being developed, and right now I think there's 6 different potential architectures, but the whole idea behind it is to find habitable worlds. Literally, the mission statement is to find, I think, 25 Earth-like planets, and to really look at those planets from every kind of perspective, from the interiors, which is part of what I'm doing, from more of the stellar dynamics perspective, from the stellar star dynamics, the planet and the star dynamics, from the astrobiological perspective. In fact, I am part of the working group that is really focusing on the living worlds, and so what a biosignature could look like. And so the idea is to put together all of the instruments that you would need to get the measurements that you absolutely need to confirm whether there is life or not. The slated time for this is to launch in the 2040s, but we have to start now because there are really important, there's data that we have to put together to say, like, what do we know about these stars? What will we need to know by the time we launch? Well, what data will we have to measure at the same time as the HWO observations? There's so much. And, of course, stars move, right? Stars move. So what we're seeing now with the stars that we're able to observe right now, they might actually be really a pain in the ass to observe in 20 years. So we're starting at it now, and actually I really appreciate the question because it's a very exciting, good time to be, doing exoplanets, because habitable worlds, I think, could be revolutionizing, truly.
Hi. Could you comment on considering maybe Europa as a exoplanet? I'm just thinking how it can be similar to TRAPPIST-1 or TRAPPIST-4 in terms of water-rich and then a cryosphere, ocean, and maybe hydrothermal activity beneath that. Do you have any insight for Europa back and forth to TRAPPIST?
I think it's a great comparison. Europa is going to be icier, so that's going to have a lot more issues than the TRAPPIST planets, because the ones that the people are most excited about, the water will be ideally all liquid. But I think it's a similar kind of idea where you would have a lot of water going on, but if memory serves, and again, not fully an expert, there's not as much of water as like 8%. I think it's higher than the Earth, but not nearly as much. So I think there's still room in there for there to be the active geochemical cycles. But again, we'd have to be able to say, like, whether this truly is a signature, or could it be coming from the moon, various things. So, fortunately, planetary science has been going on a lot longer than exoplanet science, which is 30 years old. And so I think we have a better understanding of what's going on with that. Holy hell, we can go there.
Thanks for all the questions. Let's thank our speaker once again, and it's time to move on.
And one last plug. I have a lot of Hypatia swag. So when after Vlad's talk, I'm happy to give out, especially to the VIPs. Also to the VIPs, I teach classes on graduate student professional development, how to give talks, how to write talks, how to do your CV, how to do research websites. Feel free to contact me. This is why it's all there. And I can send you all those materials.
Are his slides ready? Oh, okay. All right. Go ahead. Thanks, Natalie. Oh, you need a...
Better. Okay, thank you. Right, thank you very much for the invitation. It's a pleasure to be here. Indeed. So let's talk about how planets form, which is what I work on. So first, right, this is a field that is being built every day. Right, you go to you check the news. You go to the archive of articles, and there is always something new every day, right? So these are screenshots that I just took yesterday, and you can see, right, this is what's new in the field just in the past week, right? A few hours, a few days ago. I like to say that understanding how planets form is like trying to solve a murder mystery. It's like playing Clue. And we get clues from several different places, and my job is to try to piece them all together to try to understand what happened. So we have the constraints from the solar system, which is good. We have very detailed information. The problem with that is that it's only one system. We have the constraints from exoplanets, which is very good because you have comprehensive statistics from thousands of planets. Problem with that is that you only have very limited information from each one of these. Modernly, you also have protoplanetary disk observations, so we can actually see planet formation in action. We can look at the cradles of planets where they form, and then try to understand what is happening. And theory, of course, you put paper to pen plus computer models, and you can get a long way if you know what are the equations that we needed to solve. But first things first, any planet formation model must explain the fact that all of the orbits of the planet are prograde, meaning that they are all orbiting the sun in the same direction. You don't have planets that orbit clockwise while others are orbiting counterclockwise, right? Also, all the planets, they have orbital planes that are roughly in the same plane. The most deviant is Mercury, that is orbiting a 7-degree inclination. Now, the universe is three-dimensional, but the solar system seems to be flat like a pancake, right? So we needed to explain that too. And also there is a dichotomy between the inner planets and the outer ones. So the inner planets, they are small, right? We call them the terrestrial planets. And then the outer planets, they are big. So there are rocky planets in, and there are icy and gas planets outside, the giant ones. So the easiest way to obtain this configuration is to imagine that the planets formed in a disk that orbited the young sun. With that, you get all of the orbits being prograde and the system being flat. Plus, the fact that this guy here is a gas planet tells you that this disk must have been a disk of gas. So the conclusion is that planets form in disks of gas and dust. And that is, in fact, the conclusion of the 18th century. Right? Back in the 1700s, that much was already understood, that planets form in disks of gas and dust. They didn't go much further than that. So the devil lies in the details, and that's what we are left to solve. So let me first tell you why, indeed, we expect that these disks should exist. What you're seeing here is a simulation of a giant molecular cloud from which stars are formed. It's one of these big clouds that are in the Milky Way. In this simulation, this was a cloud of 50 solar masses. And what you're seeing is this cloud collapsing under its own weight. Right? You have some regions that are higher density, some regions that are lower density. And then soon, in the regions of very high density, we're going to see stars forming. First, I want to rotate that to show how fancy the simulation is. And there you go. You have here the densest parts forming stars. And you're going to see that some of these here, they're going to form with a lot of gas around it. So this disk seems to be just a consequence of star formation. The gas has to flow in to form the star. This gas has to conserve a rotation, or in jargon, angular momentum. And therefore, you form these disks here around them. Good. So if the simulation is right, if the theory is right, indeed, we should look at the night sky and see those things. Indeed. Well, let's try to find them. So if you go in your backyard in the winter, you're going to see Orion. Right? And all the stars there, Orion's belt, Betelgeuse, and there is one star there that is not a star. That's Orion's nebula. This is how it would look from a very good backyard telescope. You already see something, but not much. But we can do better than this. We can go Hubble on it. So this is what you would see. And this region here is a region where stars are being born right now. Right? It's a region of star formation. So let's see if we can find some of these disks there. Let's zoom in and try to find them. Let's zoom in, and zoom in, and zoom in, and zoom in. Oh, there we go. Now we found a disk. So this is a circumstellar disk. It is dark because of this lane of dust that is in there. If we could get very close to it, this is what we would see. Right? A star in the center, and then this big lane of dust all over that. It is in this disk that planets are taking shape. So the idea is that we should start with asteroids. So in some way, asteroidal mass objects form out of this disk. They coagulate from this disk. And then they keep growing, and they form Earth mass objects. Objects of the mass of Uranus and Neptune, 10 Earth mass objects, and then keep growing and then form objects of the mass of Jupiter and Saturn, which is about 100 times the mass of the Earth. Now let's see here. Why is it that we would expect exactly this kind of planets to form? For that, as Natalie said, we need to look at the chemical composition. So this is a plot of the chemical composition of the sun. Right? I should have given a quiz before that to ask you what is the third most abundant element. Usually when I ask that, what is the most abundant element? Everybody knows hydrogen. The second most abundant one, helium. Then you ask the third most abundant one, and even astronomers sometimes answer lithium. That's not. It's oxygen. Right? Oxygen is the third most abundant element. The next one's carbon. Then you have neon, iron, nitrogen, and these other ones. So the chemical composition of the sun, as you see here, matches pretty well the chemical composition of asteroids. So this is what is in the sun. This is what is in the asteroids. You follow here this line of one-on-one of most chemical elements, apart from a few ones. Helium, of course, yeah. The meteorites don't have them. Hydrogen. The volatiles seem to be missing, right? Makes sense. And to simplify this, you can go from the periodic table that you know from chemistry. Astronomers, if you are not Natalie, of course, don't really care much about that much detail. We are simple-minded people. We just call them all metals. So they're hydrogen and helium and metals. The planetary astronomer goes into a little bit more detail. Right? You have hydrogen's nearly everything in the universe, helium, everything else. And then you have the CNO that makes the ices, carbon, nitrogen, and oxygen. And then these things here that make the dust. So that's all that I need to know. Hydrogen, helium, ice, and dust. And why is that? Because that's what you get when you put this in a cold mixture. You have hydrogen and helium, right? These stay in the gas phase. Water, ammonia, and methane, that's CNO, right? Combine hydrogen with carbon, have methane. Hydrogen with nitrogen. You have ammonia. Hydrogen with oxygen. You have water. And then everything else here, right? Yeah, you have this 2%. That's just everything else that is not hydrogen and helium. And even that, most of it is not rock, right? You only have iron, magnesium, silicon as a fraction of a fraction, right? Most of this 2% is actually carbon, nitrogen, and oxygen. There we go. You already know why you formed these planets then, because from the iron, magnesium, and silicon, you form the rocky planets. If you are in regions of the disk that are cold enough, then you can condense the CNO, the volatiles, and form ices. Then you form the ice giants. And if you get big enough, you can start attracting the hydrogen and helium, and then you form the gas giant planets. So how do you get to the parts of the disk that are cold? Well, Just like in a winter day when you drive, you see that there is a line here above which you have ices and below which you don't. Same thing happens in a disk. Disks also have this snow line. Close to the star, temperatures are very hot. Far away from the stars, temperatures are cold. The ice is condensed. So then we have this rough idea. These planetesimals, these asteroidal mass objects, are forming everywhere. Close to the sun, they are rocky. Far away from the sun, they are icy. And there are more ices than there are rocks. So you end up building bigger planets in the outskirts of the system. And if they get big enough, they accrete to the gas and become a gas giants. So that was the idea of planet formation that we call core accretion. You start from the dust, coagulates into planetesimals, and then these planetesimals accrete, forming rock planets. If you have ice, you can either become an ice giant or a gas giant, depending on how big the seed gets. If it gets too big, it starts accreting gas. Great. But you can imagine this first part here is the one that I glossed over a lot, right? How to form the first objects, how to form the asteroids. Well, let's go back then to this picture. We have this disk of gas and dust. Planets are not yet formed there. Even the planetesimals are not yet formed. All you have are dust, the interstellar dust grains. Right? Now, you have to start forming planets from this. Right? This is what you get if you don't clean your room. Right? Now imagine that you don't clean your room for 10 million years. How big these dust bunnies will grow. Well, there are people that are running laboratory experiments to try to find out what happens when you collide these dust bunnies. First, they start to compact, and then you put them in a low gravity, a drop tower experiment, and then find out what happens to them. And it turns out that you have 3 possible outcomes. Either they will bounce, or they will stick. You see here, there is a sticking collision, or they fragment if the speeds that they meet is high enough. So you put the results of these 3 possibilities into a model and find out then, try to find out how big these dust grains will grow. That's what this model here shows. And if I get to the right, so what you have here is the distance from the start, and here then the radius of the dust grains in centimeters. So you start from interstellar dust grains, are the ones that you have here, micron size, and you grow them. As you see then, you grow them to about centimeter size before something happens. This line here is a line where these grains start to drift towards the star, because they start to feel the gas drag, a drag from the disk, and then with this drag, they all are lost to the star. So if this is the full picture, then planets shouldn't exist, because you lose all of the dust to the star. But last I checked, we are standing on a planet, so I guess I have pretty good evidence that planets actually exist. Right? So that's when we say that there must be something wrong here. We must be missing something big. And what we seem to be missing here is that this drift of the dust grains towards the star is not orderly. It's actually turbulent. This is a model here where you're following the drift of the dust towards the star, and as you can see, you have pockets of high density and pockets of low density. This process is called streaming instability. I think it is a horrible name. We should think of something else. Right? But it's called streaming instability because you have streams of dust that are going through the gas. So streams of gas and streams of dust. The idea here is that in the regions where you have highest dust density, maybe the same process that happened to form stars, you don't form stars everywhere. You only form stars out of the densest parts of the cloud. In here too, you would form the asteroids out of the densest parts of this calculation. And indeed, that seems to be what happens. In a model where you solve for the gravity of these dust grains, even though an individual dust grain is too small in mass, does not have enough mass to attract others, if you put a lot of them in the same place, their collective gravity gives you enough glue to bind it. And this is what you see here. This is the most massive object that formed here in this calculation, and that's about 3 times the mass of the most massive asteroid series. So this seems to be indeed a way to form asteroidal-sized objects, aka planetesimals. There we go. So you have then the first update on this idea. So this core accretion idea, I should have said, that was idea 30 years ago. A more modern view then shows that what we have is that you start from these small grains. They can coagulate up to about centimeter size, and then you have this hydrodynamical process to form the first planetesimals. Now, when the first planetesimals form, these grains are still there. They will scoop up these grains to form then the cores of the giant planets. And then the rest of the picture follows. So this seems to be a nice idea, but all that I showed you so far is hydrodynamical simulations. I'm a theoretician, I love that, but of course, the proof of the pudding is in the observations, right? So what does nature has to say about this? And by nature, no pun intended, but this was a cover of of Nature Astronomy. How can we verify the streaming instability hypothesis? And for that, I bring in my friend Pluto. I work at NMSU. As you may know, Clyde Tombaugh worked there. At NMSU, we sign a contract that every talk we give, we have to mention Pluto. So there you go. That's the mandatory Pluto picture. And I noticed, actually, that in the program, there are several sponsors named after the planets. I was looking for the Pluto sponsor. Where is the Pluto sponsor? Oh. Well. The Kuiper Belt is a region beyond the orbit of Neptune where Pluto lies. Pluto is not the first, it's not the only object, but it was the first object to be found there. And it's in this region where you can find pristine planetesimals. I would say that if the planets are the building, and you want to understand how the building was built, you need to look for the bricks. The Kuiper Belt is where to look for the bricks. So why am I saying that? We think that what happened way back when is that the primordial Kuiper Belt was a lot more massive than what it is nowadays, about like 20 times more massive. And the orbits of the giant planets evolved. The planets form and then they start to migrate. They scatter planetesimals and they migrate a little bit. And at some point, Jupiter and Saturn crossed what we call an orbital resonance, where the ratio of the periods is integer. That ends up exciting the eccentricities of these planets. So Jupiter and Saturn going into eccentric orbits excite also the eccentricity of Uranus and Neptune and make Neptune plunge into this original Kuiper Belt. And then we have the configuration that we have nowadays. So the structure of the Kuiper Belt nowadays shows the migration of Neptune in a dynamical imprint on the semi-major axis and eccentricities of the objects that we see that. So what you see here is the structure of the objects in the Kuiper Belt. This is in semi-major axis and here in eccentricity. We call the objects between 40 AU and 50 AU. So Neptune's at 30, right? Pluto's at 40. In between 40 and 50, we have the classical Kuiper Belt objects. The resonant objects are the objects that are in resonance with Neptune. Pluto is actually in a 3-to-2 resonance with Neptune. For every 2 orbits Pluto does, Neptune does 3. And then you have the scattered. This line here is the line of constant angular momentum as the object is scattered by Neptune. As you see here, is anchored at 30 AU, which is the orbit of Neptune. The objects go all the way there, but they come back here, right? And then the centaurs, which are objects that are in between the orbits of the giant planets. They have the characteristics of both asteroids and comets, which is why we call them centaurs. Now the classicals here, they are subdivided into dynamically hot and dynamically cold. And that's based on their inclination. So they have already very low eccentricity. The red dots here on top of that have also very low inclination. So orbits of very low eccentricity and very low inclination is just like the orbits of the planets. So these objects never get close to Neptune. We can tell that they never got close to Neptune to have interactions with it. So they probably form where they are and have been in deep freeze ever since for 4.5 billion years. These are the only pristine population of planetesimals in the whole solar system. So if we want to know how a planetesimal looks like, that's where we need to go. That's the cold classical population. Right. And that's what the New Horizons did. So the New Horizons was launched in 2005, did the flyby of Pluto in 2015, almost exactly 10 years ago. In fact, in July now, we're going to have a conference of the 10 years of Pluto. And after Pluto, it continued, right? It didn't stop there. It was just a flyby. And to continue doing science, he looked for objects in the path. And he found some targets of interest that it could fly by. There was a campaign to find objects on the path of the spacecraft so that we could have a flyby. This object was found then, Arrokoth, that would be on the path of the spacecraft. This shows here an occultation of this object by stars, right? As it moves, it can occult a star, and then from that we can learn about the shape. So this is what the shape looked like. It was a bilobate object, and indeed, as the spacecraft approached, it showed that it is a contact binary. It's not a single object; it's two objects that somehow got into contact. You may have seen that in the news. They called it a snowman. Right? It's 20 miles across. Actually, the shape, after you moved past it, showed that the shape was not actually spheres, at least not two of them. It was more like an oblate thing. So instead of a snowman, it was more like a walnut and a pancake. So what is interesting about this is that still you had somehow a contact binary. You have two objects, right? How did these two objects formed? And send us back to the drawing board. We didn't expect that there would be objects out there that would be in contact. And in our models, embarrassingly, we never cared about looking for binaries. So send us back to the drawing board to look in our models if the fraction of binaries that we formed was the same one that was seen, if we could explain how this object looked like. What you're seeing here is the fraction of binaries in the Kuiper belt that are orbiting prograde to orbits that are orbiting retrograde. So all of them are orbiting the sun in the same direction, but the binary may be orbiting each other clockwise, anti-clockwise, counterclockwise, or clockwise. Right? So these are prograde and these are retrogrades. Turn out that there is about 80% prograde and 20% retrograde. So as a theoretician, what do? We go back to the model, run again the calculation, and then pay attention to how many objects that are formed, how many planetesimals that are formed here that are binaries, and how many of these are orbiting prograde, and how many of these are orbiting retrograde. So you see here, some objects are forming, right? Some of them actually here you have a collision and all, and this is what comes from the simulation. In solid line here you have the result from the simulation. In dashed line you have the observations, and they seem to fit quite well, right? So the models indeed give you about 80% prograde objects and 20% retrograde objects. So we have here then the cartoon idea of how these objects form, right? About 4.5 billion years ago, the streaming instability formed these objects and formed two objects in orbit around each other, and then eventually they got into contact. Of course, this eventually also needs to be calculated. This is a simulation done by colleagues of mine in Australia. You see here the the more massive one, the less massive one. And as you keep following this calculation, they will affect each other, and eventually you will get to contact. What is amazing by this is that these objects are so low mass that you have a constraint on how slow this impact must have happened. There are no large craters there that would be formed by a high speed impact. Right, so you can constrain the speed of impact to about 2 meters per second. That's like 6 feet per second. That's human walking speed. It's like me walking here into this wall. You know, that's how fast or how slow these two objects got into contact, and we can reproduce that in the models. Sorry. Stop right as it was getting into contact, right? Yeah. There you go. Almost there, and then stop. Right. That's true. That's true. Right. So I have 3 minutes left. Let me talk about very briefly, about another piece of evidence that we get that we can see about how planets form, which comes from observations of ALMA. Right, ALMA is the Atacama Large Millimeter Array, and we also have observations done here in New Mexico with the VLA that have been a complete game changer. Why do we need to go to these wavelengths? Because of course we have more information in these wavelengths. And ALMA gives us a resolution, right, that we couldn't otherwise get. So this is here the solar system, and this is what it would look like, right, in resolution if you put it about 450 light years away, which is the distance to the nearby stars. The nearmost region where stars are formed now. So this is what we could do before, right? 0.3 arc seconds, and this is what ALMA can do now. In actual results, so this is what we had before ALMA, right? The best picture that we could have before ALMA, and this is what ALMA can give us now. So the resolution that we get is just amazing. This is a more complete view, right? Other disks. And this is just, I mean, the first time I saw this, I was jumping, you know, like, oh my God, like so so exciting, all of this information that we have here. I'd like to focus on this object here, NWC 758. And what you see here are these blobs, right? These blobs are blobs of dust. Something is trapping the dust here. These things are probably vortices. Now, vortices are an ubiquitous fluid mechanics phenomenon. We see them in the atmosphere of the giant planets, as whirlpools in the ocean, right? On the atmosphere of Venus, on the pole, you have here, right, this double vortex. What is interesting for me about the presence of these vortices in disks is that they can trap grains. As I said, the grains, they are drifting towards the star, right, in a disk. If you think about these vortices as a mini disk within the disk, any dust grain that is trapped there would also move inwards. But in the inside, but in the center, there is no star, right, to burn them. So you just accumulate them more and more and more, and you end up forming planets. So this is a calculation here that I did, showing what happens when you have a vortex in a disk, right? And then you trap dust grains inside it. And what you see here is already some planets forming, right? So it's going to form more and more. When you measure the masses of these objects, this is what comes out of the calculation. So this is a Mars mass object, a Moon mass object. So it's a way to form a Mars mass planet. So I'll stop here, and I'll take any question now. Thank you very much.
would have loved to see that go on a little bit more, but I think we do need to move on. Thank you very much, Wladimir. So yes, we have some time for questions.
So there was the earlier talk about the TRAPPIST-1 system, and it showed multiple planets. So have these models, planet formation models, been evaluated against some of the information we have about these exoplanet systems?
Yes. Yes. For that, we needed to introduce another ingredient, which is the planetary migration. Right. So the planets are formed, and then they interact with the disk. So they will not stay at the same place where they form. These objects, they are formed. They are now seen quite inside, right? They are very close to the star. So there is a question: did they form there, or did they form elsewhere and moved inwards? Right. There are a class. There is a class of planets that are called the hot Jupiters. Right? There are planets that are about the mass of Jupiter, but they're quite close to the star. Right? These ones very likely formed much further out, and then migrated all the way into where we see them. On the case of TRAPPIST-1, I was actually quite interested, in the talk in the information that Natalie said, that those objects have too much water. To me, that's a sign that they formed beyond the snow line, right? So you don't expect an object that formed in the habitable zone to have that much water, right? Like the Earth. We don't know exactly where the Earth formed, but definitely not beyond the snow line. So to me, that's a sign that those planets formed beyond the snow line and then migrated into where they are now.
Lovely talk, very visually stimulating as well, so thank you. Back when you were talking about with the Kuiper Belt and like Jupiter and Saturn were kind of in this nice equilibrium where they weren't going too far out and destroying things. What triggered them to get out of that equilibrium? Was it something natural, like they just kind of got further and further away until they hit that breaking point? Or do you think something actually, I wouldn't say unnaturally triggered it, but like they got hit by something?
Right, so let me show it again here. Right, so as you see, they are in these orbits to start with. They change their orbital position because they're scattering asteroids. Every little asteroid, every single one of them, right? Each one of them doesn't have enough mass, but they have a cumulative effect. You scatter one, the orbit changes a little. You scatter many, the orbit changes a lot. Essentially, what happens is that the orbit here has to conserve energy, right, and angular momentum. So whatever energy it takes from the orbit of the asteroid must be given to the orbit of the planet, and vice versa. Now, you would imagine that if you scatter inward or outward, on average, the orbit doesn't change. But what happens is that Jupiter scatters preferentially outwards, right? The Jupiter will scatter asteroids to outside the solar system. So in this case, it will preferentially migrate inwards. And this motion will eventually lock it in resonance with Saturn. And when you get to resonance crossing, that's when you pump eccentricities, right? It's true that Saturn and Uranus, they scatter both inwards and outwards. And Neptune, it doesn't have enough mass. So if it scatters outwards, it's going to come back. Jupiter has too much mass. If it scatters outward, the orbit, the asteroid does not come back, right? So you end up with a net inwards motion.
Okay, I guess it's time to move on to the panel discussion, and I would like to invite all the speakers from this afternoon's talks to sit down here in the front. The speakers from this morning's talk can stay where they are, but we expect or hope that some questions will be directed to you as well. So be prepared to respond from your seats. Thank you.
Are we on? There we go. A simple question to the last speaker from NMSU. Can you give us a sense of the type of computing resources it takes to do those simulations? Are those supercomputers or laptop clusters or?
Hi, thank you all. I was curious, this question might pertain to the two in the exoplanet session. How might a captured body, either its atmospheric composition or its orbit parameters, differ, and we can tell us a detached body from those sorts of properties compared to the ones that formed in our system?
Okay, so captured bodies, very exciting. Great question. So one, you can look at the dynamics of them. So captured bodies might not actually orbit in the same direction. So this is going back to what Vlad was saying with like the prograde versus retrograde. So very interesting thing in our galaxy. So not even exoplanets, but in our galaxy, there's actually a thin stream of material on the outside that's going in the opposite direction of the rest of the material, which means that it was like pulled from probably a nearby galaxy. So if you look at the orbits alone, that is an excellent way to get a sense of it. But yeah, so for the composition of them, if you capture something, it might not have anything to do with the same material as the host star. So you do have to look at the dynamics of the system to get a better sense of it. So in our own solar system, most of the planets are fairly in the same plane, but some of them are like pretty wonky. Uranus, what the hell's going on with that? Lisa? Yeah. And so from that, you have to sort of use both the dynamics and the composition to get a sense of of what's happening. Because if a planet's not formed with the star, then you can't go start a planet. That it just ruins the whole thing. And so you really have to look at, again, everything together, the whole system and the way that it looks, to see like when that relationship might work and when it might not.
It's fascinating because you guys all brought up this idea of chemistry, and without chemistry, there's nothing, right? So
I'm going to quote you forever on that.
no, and I'm gonna quote you because you say something that is true. Very simple, right? We only have one data point, and you start talking about the abundance of water, what it means, and then Wladimir talks about the grain collisions and the beautiful simulations. And then we have photosynthesis, photooxidation, and all that got me thinking back to the very basics that my memory can take me, the original life on Earth. And I was thinking of Uri Miller and operating and handling, and how all that fits into this idea. Why keep looking at water and carbon, when we can look at all these other elements, phosphorus, silicon, and how does it all fit into the whole story that we're making up as with simulations? Is it possible?
No, I totally agree. In fact, okay, so we're able to look at different elements inside of stars now, and this has been going on for like probably 40, 50-ish years. But before that, the easiest thing to measure inside of stars was iron. Iron is very prevalent in stars, and there's a lot of absorption lines all over like the optical spectrum. So it's just super easy to see. And so for a long time, astronomers particularly, they looked at iron and used it as a proxy for all of the other metals, as Vlad was talking about, within the star. And so even now, astronomers will say like, oh, we're looking at the metallicity, but they really mean iron. And I'm like, why are you only looking at iron? We can look at like literally 100 different elements. We can get direct, comparison of magnesium and silicon and nickel and a bunch of other things. And yet it's still, people just look at iron, and it just kills me because I'm like, we're way beyond that now. We can actually try to get to models and really dig into it. And so I think it's just like anything, and I'm sure most of the people in here would kind of understand this, it takes a long time to change a field. And to really get people on board to see it, to change their own research programs, to be like, you know what, I was going to go on this track, but I think this is more the future, or this is where I think we can all go together to really get to these answers. And that's the hard part, is getting people on board and actually changing their minds, changing their research, and changing where they think they're going to go. But it's difficult for anything because, yeah, people get stuck in their ways. They don't see the papers. So that's one of the reasons I love giving talks. I'm like, you can't ignore me if I'm right in front of you making jokes about all these different things. So.
I mean, I think it's a good point too. Just that, what is life as we don't understand it, and that is really important. There are things that life does, and we can think of, chemical mechanisms that could work with different chemistries. And I will say though, the reason that we look for life as we do know it is because, first of all, it's right here, but it's amazing. I think we've seen this in this session. The elements that make up life are actually incredibly common. They're not exotic. They're not rare at all. And in fact, I don't know you could probably speak to this more, but there are clouds of amino acids in space. This stuff is everywhere. And so it makes sense to me that we're made of the things that are here, right? It's like the stuff that was available and not something very unusual. And that's probably why, I think yesterday people were like, okay, who thinks there's definitely life somewhere else? I mean, I don't know why everyone else raised their hand, but that's, for me, a very compelling reason to continue to look, because all of these chemistries that, that make up life as we do know it are actually incredibly common throughout the observable universe. And so, if they're here, they can be used, and we know that they have been used. That isn't to say that we should exclude new ideas, which we should absolutely continue to do, but that might explain why research is focused in that way.
So actually, that was great because it connects all of you together. And so maybe one of you can comment on the composition of Bennu, that OSIRIS-REx went and picked up pieces of a planetesimal and brought it back to Earth in its pristine form, so we were able to look at it. And anyway, take it away.
I don't know if I actually remember the composition as well as you might, but it is kind of amazing, right? One of the things, actually, here's a question. I'm going to just pivot here. Where are the chondrules? Where are the chondrules, people? So for folks who don't know, chondritic material makes up most of the leftovers of the solar system that didn't get incorporated into a planet. And so chondrules are these little blebs of materials. And so Bennu is like, kind of a big dust ball that so it didn't get made into a planet. But that's what I thought was, and maybe I'm naive, so a meteoriticist probably can tell me why I'm wrong about this. But it is interesting that we don't see that there is still something unusual. That being said, that the composition is, in fact, it matches sort of the bulk composition of the solar system pretty well, which is something I think we would expect. And I think there are organic compounds, simple ones, not complex ones, but they are there. And so that just tells you, if that's in the leftovers, what do we get? We got a lot of good stuff. Yeah.
I mean, in the end, it's all photochemistry, right?
Yeah.
So, but the bottom line is that we need the collisions to build the dust bunnies to form the planets, and the chemistry gives us what Bennu told us is all the not all the amino acids, many amino acids, and the basis of basically ribose for RNA and eventually DNA, and a bunch of other really interesting small organic molecules, which in the early Earth, and we had early and late bombardments, so planetary protection, we didn't want to be protected from those bombardments because they delivered all the elements that we need to create life, along with the planets forming with the schnapps.
Yeah, keeping it spicy. Thank you.
So can you guess what I'm going to ask you? This is a question for each of you to respond to. What do you need to do to be a planetary scientist?
You're looking at me, so I think you're starting on this end. I mean, we start in the middle. Yeah. I mean, I think the first thing that you need to do is just be passionate about it. I saw a comet when I was a kid, and I just wanted to know more. I didn't know how to do that. I honestly had no idea. And then, there was the Pathfinder mission to Mars in the 90s, and I was like, that's awesome. Like, I totally want to do. I had no idea. I think the just don't feel like you have to give up your childhood dream. You can figure out how to make it happen, and I if I could tell my childhood self that I work on a spaceship with lasers, I mean, she'd be like, no way. Like, it's true. So I think just, and understanding that opportunities will come your way, and you don't know what's in your future, but take those opportunities when they come. Don't be afraid to be curious. Don't be afraid to talk to people and ask. Again, don't be afraid to call somebody every day for 2 weeks until they give you a job. I shouldn't even say that. Oh my God. Yeah. Well, yeah, Bill did. I don't know why. Mistake. Yeah, but that's it. Like, it's you don't always have a straightforward path. I think that will probably be the theme as I pass this microphone down. We all had this passion and joy for something, understanding the universe, and we didn't know how we were going to contribute, but we knew that we weren't going to give up, right? We were going to keep finding the way that we were going to do that. And I think we've all done that in different ways. So your path is like this, but you can, just believe in yourself and don't give up on that passion, and take the opportunities as they come.
Yeah, I mean, I can echo all the same sentiments that, you really need self-confidence and to not give up. And that's really important, because there are many times when you're in school for those 24 years that you're going to feel like I'm out of here. I'm not going to pass this test, or I'm not going to get this funding, and there's the end of my career. But you always have to be confident enough to stick with it, and again, it's the passion. I mean, if it started with me from collecting rocks as a kid and then wanting to do planetary geophysics, I mean, that's what leads you to your ultimate path. But it's also wanting to live an extraordinary life. I think you could be a type of person who's very curious about the world around you and be inspired. Back when I was a kid, it was, Astronomy Magazine and all those absolutely gorgeous pictures of the mysteries of the universe. And I couldn't imagine a more cool career than trying to figure out how the universe works. And so it's that kind of passion, but I think it's really wanting to live that unique life that contributes some meaningful way to our understanding of what's around us. And also math.
All right, I'm gonna echo the sentiments. So passion, also determination, persistence. I actually consider determination and persistence to be like one of my major strengths. I will not stop, won't stop, can't stop. Math, computer skills, 100%. Like I had to learn how to code. I put together a multidimensional database that does not exist in astronomy. Computer scientists laugh at me, but astronomers had no idea what I was doing. So computer science, 100% do that. But the other thing is look for the opportunities. Like they're out there, the materials to help you get through the things that you need to do the internships, to find the people who do the things that you do. Like it might not be at your university, all universities are different, resources, different people. And if it's not, if the things that are there aren't what you want, they exist. So like look for it. I put so much of my stuff online just to make it available to people. Both of my parents are actually professors. And I said for years I would not be a professor. So I didn't actually. Like my path was like all windy and stuff. Hilariously, my parents are also earth scientists and like geologists, and like the irony of all of this is just wild. But look for the stuff that's out there. If you are having imposter syndrome, like look for resources about that. If you are excited about an internship, working at NASA, working, you know, at different places, look for those things. Reach out to the people and say like, hey, this sounds awesome. How do I do this? Maybe not call anymore, but you can email a lot. Emailing works too. So, but like there's a lot of stuff out there. So find it, and people will help you. Like they will become invested in you. You know, how many people like here had other people invest in you, and this is why you're here today. And so like it's the sort of the pay it backward sort of thing. Like so reach out. We are all here. Probably all the more senior members here will help you if that's what you need, because we want you to succeed. We want to see ourselves in you. We wanted us to succeed. So we're going to continue that for you.
I will echo the sentiment here too, that the main thing is passion. I got interested in astronomy when I was 5 years old, and that was I opened a book. It was the science book of my sister that was on 3rd grade. Back in the 80s, we didn't have a Wikipedia, we didn't have the internet. If you wanted to know something, you needed to reach out to the books, right, to the encyclopedias. I opened the book just out of curiosity, and the first page was a drawing of the solar system. It wasn't a fancy picture. It wasn't a a photo from Voyager. No, it was just a photo. Right? Sorry, a drawing, and the drawing had the sun, the Earth, the Moon, and the planets. I recognized Sun, Earth, Moon. The others I had never heard of. Like, what are these little balls with funny names? But the realization that those were other worlds like the Earth hit me with a force that is hard to describe. So as you heard, that's a very common thing, right? I think that it's fair to say that scientists are frequently made in an instant like that, right? When you get mind blown by something, and from a curiosity becomes a passion, and from a passion a life goal, and you keep it that. I mean, if you keep it that passion burning, right? Then yeah, that's the recipe. Now, when there are going to be challenges for sure. So yeah, you need grit, you need resilience. I think that I was lucky to find through school and college that I liked math and I liked physics. But if astronomy was what it was back in ancient Greece, what it was in the Middle Age, I would still be doing it, because our goal is to understand how the universe works, right? And we are going to use whatever tool is available to understand it. With that said, then I think that one major thing is to pick something that you really like to do. If you have a project, I've seen way too many people pick a project. I mean, like, they didn't pick it. It was a project that was given to them. It's not something they were passionate about, and that ends up killing an enthusiasm, right? So work on what you love.
I'll make this quick because we probably all want to go to dinner. But this is kind of a continuation of the things you guys just explained, and I know a lot of us in this room got interested either looking up at stars and planets or looking down at rocks and other things on Earth. But we all have this similar interest when we were younger. But what did you guys have to do to combat the realization when you did your undergrad research, grad research, when you did your first professional level research, that what you thought this career was like was writing code, doing simulations, reading papers, doing database things, being in the lab, which kind of may have shell-shocked your younger self. we've talked about passion, persistence, determination, grit, but I want to know if there was anything specific that you guys utilized to get past that reality check.
That's a fantastic question. So thank you for asking. Okay, I did not like coding when I first started, and hilariously, the first project that I worked on was actually magnetohydrodynamic simulation, very similar to what Vlad did, but making stars. And what I wanted to do was to deal with the chemistry. I did a bunch of internships that helped me sort of whittle it down of what I was actually passionate about. So when I started coding, I was like, oh, wow, I hate this. This sucks. Because I didn't understand it. I was sort of tossed in the deep end. I was given code written in Fortran 90 to look at, and it's painful. And no comment. No. So I didn't like it. But what I do like, I like figuring out little puzzles and stuff. And so that was what I sort of thought of it as. Okay, I wrote a thing, it's breaking, but it's something fun to figure out when you actually view it like that. So I sort of changed my own mind about it. And this is true for me. I go rock climbing. It's just a little puzzle to figure out. I like doing puzzles, those sorts of things. So you might not like it initially, but give it some time and you'll find that these things kind of grow on you sometimes. And if it's not what you wanted and you do it and you're like, wow, I really hate being in the lab or something like that, there's other ways to attack the same problems. I mean, how all of us here actually tonight, we all came at this from wildly different perspectives and stuff. I actually thought I was so awesome. Nina's talk, we talked very similar things, and we came about it in very, very different ways. And so there's other ways to attack these same things that you are passionate about. It doesn't have to be theory. It doesn't have to be in the lab. It doesn't have to, I kind of do everything. So but so you can find how to get there. There's a lot of pathways, not just in your academic career, but also to the science you're interested in. And so you just have to find how to get there overall. So.
I'm going to cut you off. And
Sorry.
I'm going to invite you to keep the conversation going. We have a break now till 6:30. If you are part of the crowd approved to be in the speaker's lounge, the food there starts at 5. So you have a little bit of time here. The food will be on. Keep talking, okay? And then we'll come back here 6:30 for the evening lecture. Thank you very much.
Come find me for swag. I have it now. This is your time. Sweat time. I don't want to carry it all home. I have a question for you.
So, I think I'm going to listen online. I have to because my son is. I'm going to try to drag my son here. My husband has something to do.
I'm just looking for somebody to help Paolo run around with the microphone. And you're on the committee, but maybe we'll get Lisa to do it.
I'm sorry. It's only because my son is 7 and he's
Okay.
You don't have to explain it.
He's not here today because he's like, oh, it's just my mom talking. I don't want to hear that.
Okay. I'll get her to do it. She looks excited.
I'm sorry.
Don't
I'll
worry.
be there on
Don't
the
worry.
internet.
Don't worry.
Wait, the who now what? Oh, wait,
Are you coming tomorrow?
yeah, I'm planning on it right now.
Paolo with the microphone. Like somebody helped you. He's the session chair.
Oh,
We just
I
need
see.
another person to
Oh,
help.
yeah.
I was going to have Nina, but she's not able to come tomorrow. So.
I'm planning on it right now. Let me see what's happening with my home guests.
Okay, so if
and
that
what's happening.
plan fails, I will get
Plan
someone
B.
else.
Okay, yeah, yes,
Okay.
I'm happy to do it if I.
Okay, I just don't want to leave him all on his own.
Okay,
Of course. And I would be super. I mean, I'll try to bring.
Yeah,
I'll
because
try
I'm
to bring my
like,
child.
losing
I will
track
try.
of those numbers.
Quick cryptic questions.
Oh my God, look at all this! Look at all
I
this
know
goodies.
she brought like mini things. I know she. Like, yeah.
Okay,
It's
thank
awesome.
you.
Yeah.
Goodies. Don't forget your.
Thank you.
be bad if you walked out of here and left that for me. I would auction it off. What happened to my? I had one more. Oh, here.